All right. Hi, everybody. So you might have heard of FlexAttention, which is a pretty popular thing that came out of the PyTorch team recently. Um, and today, Boyan, who's one of the authors of FlexAttention, is going to introduce us to this. Take it away.
Okay, cool. Yeah, thanks for introduction. I'm Boyuan. I'm working on some performance in PyTorch Compiler, especially FlexAttention. Let's start now. Okay, so we all know attention is very important, right? And so basic attention, we take the query key value, we compute a matmore between q and k, then we have the softmax, and finally multiply with v. This is the attention. Attention is very important. It accounts for a significant portion of latency for transformer. That's why we have the flash attention. Flash attention is the most important optimization for attention. Basically, it fuse everything together into a single kernel. And we can see on the right-hand side, comparing the latency of PyTorch implementation versus flash attention, we can see flash attention is much faster. Okay, uh, so so people want to have different attention variants for many reasons. Let's say people start with causal mask, which means, oh, a query token can only attend to the past K token. So, it's like, oh, when we say a sentence, we rely on the past word to infer the next word. After that, people also have the sliding window mask, which means, oh, I don't need to refer to so long context. Some recent context might be sufficient. And we also have document mask, which is we have multiple documents at the same time, and we only attend to the token within the same document. So in this way, we can see there are many different attention variants. Also, people may want to say, oh, I want to encode the relative position of two tokens into the attention,
Mhm.
or the alibi bias may, multiply this relative distance with some other trainable or some other bias, right? So basically, we have lots of different attention, but it's very hard to hunting all attention variants. Many times when a machine learning researcher propose something new, they may not have the expertise to manual tune the kernel. So they probably, okay, say find some GPU expert and ask them to spend 1 or 2 weeks to write a good kernel. Then they use this kernel to try, and sometimes this new variant doesn't work. So the GPU expert like with 2 weeks of work, right? So it's very hard to do that. That's why we want flex attention. So basically for FlexAttention, we have an extra score mode to allow the modifying the softmax result to say, oh, use this attention in a very different way. And what is a score modification? Basically, it takes the score, which is the original, like the score matrix. Then we say for the batch dimension, head dimension, query index, KV index, how do we want to modify this score? So it's actually very flexible. Cool. So what can we implement with score mode? Let's say the relative position. We can just say score plus Q index minus the Q index, which is the relative distance, right? We add it with the score mode and say, oh, now we have the relative position information. The good thing is we don't need to materialize the relative position bias as a full tensor, right? So we can avoid the quadratic memory usage and achieve a better performance. You can say comparing with the scale dot product attention SDPA in PyTorch, the flex attention can actually have a much better performance because of that reason. Another, also for, let's say, for the alibi bias, we can say, oh, alibi bias with the shape, which is a tensor of num heights. Then I have the score. I just plus this bias, then multiply by the relative distance, right? So in this way, you see with only two lines of code, we can implement the alibi bias very easily.
So yeah, let me ask a question. So it seems to me that okay, so there are two things that are interesting here. So one is you started with a handwritten flash attention kernel, right? And then you talked about many variants of it. So uh, one of the things you're trying to address is that people should not be needing to write their hand-tuned kernels for all of these variants, and then more variants are going to come in the future and so on. But the other arguably like equally interesting observation that you're making is that by modifying one part of the attention like mechanism, it's sort of like sufficiently like general not only to model many different variants, but even more interesting is that you actually, I mean, got some performance improvements over like some bad ways of doing the same equivalent thing. Is that fair?
Yeah, that's true.
Cool.
Yeah, because I mean, in many cases, the attention variance is just element-wise modification. So with flex attention, we just modify it in the register. We don't need to materialize the huge tensor of the modification. That's why it is faster.
Yeah.
Yeah. Okay, cool. So another example is soft capping, which is a technique introduced in Java 2 and Grok 1 that prevents lodges from growing too large, right? So we can also implement in, let's say, four lines of code. Nice. So now come back to our cultural mask example, how to implement it. We can just say, oh, the Q index greater or equal to Q index. In this case, we use the score. Otherwise, we mask it off as minus infinity. Uh, this is uh, this is correct for the result, but I mean, it's not so fast. Why? Because, okay, for the upper triangular, we know it's like a minus infinity anyway, so uh, why should we still compute it? We can just skip it and make it faster. That's why we want another thing called mask mode. What is mask mode? Mask mode just takes the BH query index and the QE index and get a Boolean, say, oh, whether I want this position or not. So the difference here from the score mode is it does not take the score anymore because we only see a true or false, say keep it or not. Once we have the mask mode, we can automatically compute a block mask for exploiting the sparsity. Like, okay, so how do we implement causal mask? Say we just return Q index greater or equal to QV index. That's it. And we can use it we can put it into the create block mask, which is the API from FlexAttention to create the block mask. And later when we call FlexAttention, we have the query key value tensor and additionally provide this block mask.
So in this case, you do not have you do not implement the other like the score mod function.
Yeah, so for this causal mask example, we don't need the score mode because
Right.
for every element, it's the same value, right?
Yeah, yeah. But if
Yeah,
you wanted to combine causal masking with some other
yes, we can.
mod that you could then you could, yeah. Okay, cool.
Yeah, it just additionally provides the score mode. Nice. So how about the performance? This is a comparison. We can say if we implement with score mode, that's the performance, that's the latency. And if we use mask mode, it's much faster because many computation can be skipped. A few more example, like we can use it to implement the sliding window attention. So we have the let's say this window mask is just take the difference between query index and the QE index, compare it with the sliding window, say, oh, if it's too far away, we don't use it. Also, you see we can compose the causal mask with window mask just with some, element-wise AND operation. So this is some performance for the sliding window mask. We have the causal FA2 and SDPA plus the mask, and finally the FlexAttention. You see we have a pretty good performance. Another example is the document mask. You see we have the document ID for every query and query index. Then we use a single line of code to implement the document mask. We actually have more examples. So, okay, sounds good. Then how does it work? This is a detailed example of the block mask. Here we say we have the score mode, which is a relative position. We also have the mask mode, which is a sliding window mask. We can implement whatever score mode or mask mode. And remember, we have the Q and K. Q multiply K gives us some score matrix. Here we have two types of block. One is a full block, another one is a partial block. Full block means all the data within this block will be used. And partial block means, oh, on the boundary, some elements in this block are used, some are not, because we are using the sliding window, right? So basically, we have a line here and another line here. So beyond this line, we don't need, and within this line, we want it. That's why we have the partial block and the full block. And for the for block, we can record, oh, what's the block index we want to use for this row. For example, in the first row, there's nothing, so we put nothing here. And for the second row, we only use the first block. That's why we have 0. And for the third row, we have 0 and 1, and so on. Similarly, we have the same data for the partial block. In this way, we can encode the sparsity of the mask mode and use it during runtime. Okay, cool. A little bit more detail, like how did we do the compilation? So basically, we have defined the causal mask and the relative position, score mode. With that, we use torch.compile to trace these two functions and do the lowering to generate some threaten code, this mask and score. At the same time, we have built a very efficient attention template, and we leave two space to just fit in this generated mask mode and score mode threaten code and modify the score matrix at runtime. In this way, we can generate a very efficient code.
So, quick question. So you showed a document mask example, right? Where the functions were relying on something outside, which was the document ID, I think, right?
Yes.
So what happens in that scenario? When you trace through it, where is document ID stored?
Oh, okay. So that one is a captured tensor. It will be captured within the, let's say, the mask graph.
I see. I see.
Okay, here we have an example for the threaten template, threaten attention template. Actually, our FlexAttention can support different types of backend. Like there are some CPU backend built by the Intel folks, and we can also support like a CUDA backend or the Kafka template. So as long as people build this template, we can run the FlexAttention on different language or other things. Okay, sounds good. So we have the forward and backward and inference. So this covers many different use cases for attention. I want to talk a little bit more about inference because inference is different from forward. Why? Because for the inference, there is a unique attention pattern, like a very short query sentence will attend to a super long key value cache. The KV cache length could be 128K or even longer. So why do we have query sequence length as one? Because during inference, we will inference token one by one, right? So every time we have a single query, we attend to all the past data, then we just predict one. That's why it's like one token. So uh, then what's the issue here? Because there is only a single query token, we can no longer do the parallel along the query side, right? Also, the KV cache, the KV length is super long, so there are some potential parallelism opportunity. Yeah, that's why we have seen the flash decoding. Here we have an example. It's basically we split along the KV dimension. And yeah, so you see we split into five splits, and for every split, we do the computation in parallel and accumulate it into, let's say, five different output. And finally, we have a single reduction step to get the single output, right? In this way, we can use parallelism along the KV length dimension.
So how does this compare with like was recently hearing some kind of VLLM talks, and they mentioned like batched inference, but they also mentioned a bunch of like pipelining optimizations that feel similar. Is there overlap between these optimizations?
I think there are many different types of the parallelism, like the context parallelism, pipeline parallelism, and they are working at different level. This one is more like a kernel for the decode one single decoding step of the attention op.
Okay.
There could be model level, different kinds of parallelism.
Okay.
Uh,
So here you're talking about just like when we're generating the kernel, what kind of
yeah.
optimizations?
Yeah, exactly. So flex attention is at the kernel level. It does not handle the model.
Makes sense.
Yeah, so that's the flash decoding. We have the flex decoding using the same optimization, but we still allow the apply the score mode for the flexibility. Yeah, so a little bit on the benchmark. We can see we compare with FAKV, which is flash decoding. We can see flex attention and flash decoding, they are have similar performance. Also, we have the scale dot product attention, which is much slower compared with like the flex attention. We also integrated to the GPT fast for some model level benchmark. We try it on the Llama 3.1 8B and 17B. We can see a significant amount of speed up over various lengths. So after that, I want to talk about page attention because page attention is very important for inference. It's first done by the VRM team. So during the inference, we have the KV cache, right? We have multiple requests A, B, C, and we do inference for every request. Some requests has a long sentence, some have a shorter sentence, etc. But usually, naively, we will allocate the logical cache as a regular tensor. So we will waste lots of memory if the sentence is short. That's why we can have a better KB cache, which is a single, like a one-dimensional tensor in some sense, and compact everything, so we don't have the wasted memory. This is good, right? In order to manage the mapping from the logical KV cache to the physical KV cache, we want a page table to say, oh, for this request A and the first block, where should I find it on the physical KV cache? So this is page attention, which is very useful for saving memory and for a larger batch size. We want flex attention work with page attention. So the first thing we want is block mask conversion. Remember for the KV cache, remember for flex attention, we have the block mask to say, oh, what's the block index we should use for every row or batch index, right? We also want a counterparty with the physical KV cache. Then we can just apply it as a indirect indexing and make it work with flex attention. That's why we have the first thing called block mask conversion. I want to give you an example. So basically, you see for this attention, we have the request A. We only have the value for the block 1, 2, 4, and for 0 and 3, it will be masked off, so we don't need it. That's why we have the KV index, which is part of the block mask. For this request A, we have 1, 2, 4, we will use it, and 0, 4, we don't use it. Sorry, 0, 3, we don't use it. Because we have the page table for the mapping from logical KV cache to physical KV cache, we can do a mapping of this KV index to something for the physical KV cache as this converted KV index. After that, we use this converted KV index for the flex attention, right?
So this is another sort of primitive that you provide in the library, so that if you wanted to convert the block marks, you could by your implementing this. Okay.
Yeah, exactly, exactly. People can just call this convert logical block mask to do this transformation. They don't need to care about the details. Yeah, so this is the first step for the block mask conversion. After that, we also need the mask mode conversion. So remember, we have the mask mode. We take the batch index height and the query KV to say, oh, whether I want to keep this block or not, right? So after we do the conversion, we are doing some computation on the converted space. It's not the original space. So we also want some conversion for the mask mode. That's why we have this. So basically, we basically take the original mask mode and return a converted mask mode. And for the converted mask mode, we will take the same batch index, height, query index, but we are taking the physical KV index. After that, we do some index computation to get the original logical KV index. And finally, we call the mask mode on this logical KV index, right? This automated conversion makes sure, oh, the result is still correct. Also, user does not need to worry about, oh, how can I handle this complexity here? Similarly, we also have the score mode conversion to convert the score mode. Uh, okay, cool. So a little bit on the benchmark side, this is the result of flex attention and the flex attention with page attention comparing with flash attention V2. So we can see flex attention with page attention is similar performance as flex attention and similar as flash attention, which means there are not so much latency overhead. We actually only observe like less than 5% latency over this different sequence lengths. Also, I have a small serving example showing that, oh, we can have 76 times higher batch size with this page attention technique.
So which means that like if you're not expecting kind of a lot of memory overhead, then you would use flex attention. But if you're sort of like constrained for memory, or you want to support like larger batch sizes and so on, so then you would use the page attention variant, but then you would not pay too much.
Yes, yes. So I think in a real world serving example, the different requests have super different
Yeah.
sequence lengths, right? So that's why we want the page attention and flex attention together. Uh, okay. So we have seen some early adoptions and fortunately get some feedback, like Michael Show in the show O using FlexAttention. Also, Andrew Carr using FlexAttention for reproducing the Llama 2 7B overnight. And we have the Nano GPT training speed run using FlexAttention. Then some guy, Arthur Zucker integrated FlexAttention to Hugging Face. And we have seen it for this block diffusion training, like the Nathan FlexAttention, and yeah, the Flash Infer people also are inspired by FlexAttention to build some super cool thing. So yeah, so we unfortunately have some early adoptions. So if you are interested, definitely try it. Yeah, that's all for my talk. Thanks for attention. We have some online blog for FlexAttention for inference. We have many examples in the attention gem. Also, recently we have a MLSys 25 paper to discuss some technical details. Yeah, thanks.
Cool. Very nice talk. And yeah, so what's next for this project? Like, do you think that you're done with flex attention in some sense? The primitives are general enough that you can capture future variants, or are you working on other such kind of abstractions in other areas that are sort of inspired by the flex attention kind of a success story?
Yeah, so I would say flex attention is pretty flexible now. And one major thing to do is the performance. We can include more like new GPU features into flex attention to make it even faster. That's one major thing. Another thing is to support more use cases. So, like we may find some new optimization or opportunities as more and more people use it.
Okay, cool. All right. Thanks again, Boyan. It was a lovely talk.
Yeah, thank you.
All right. Bye-bye.